Myself, Dr. Vitthalrao Kashid, Assistant Professor in the Department of H&S in Chemistry. Today I am going to discuss about the organic name reactions, which is Diels-Alder reaction. As we know that this is very important reaction. This reaction, which is discovered by scientist Otto Diels and Kurt Alder in the year of 1928. As we know, this Diels-Alder reaction is basically the type of cycloaddition reaction. We have the one substrate as a 1,3-butadiene we can consider as a diene, and another side we have a dienophile. If we do the Diels-Alder reaction, as we can call it a cycloaddition reaction, basically it is 4+2 cycloaddition reaction. Here we will have eventually the 6-membered adduct that we are calling as a Diels-Alder reactions. We can have the examples also into the important reaction where we have getting the cyclic product. That is, again, we can start with the 1,3-butadiene as a diene, which is having a nucleophilic in nature basically, and here we will have a dienophile reactant which is in the electrophilic in nature. We start with the one driving force starting from the diene, which is in nucleophilic nature, and another side we will have a electrophilic in nature, that is our dienophile. You can see we have taken as an example, that is 2-butyl diode as a dienophile over here, and we will have a example of product over here, that is our 6-membered cyclic adduct into the Diels-Alder reaction. Basically, this reaction we can have a mechanism over here with diene as well as the dienophile. In cyclization, we will have a adduct in which we will end up with the nullification of 2 pi bonds and formation of 2 sigma bonds over in the product. That is basically our Diels-Alder reaction over here. If we have the 6-membered formation of the ring into the product in easy way, we can get the in the easy way we can have a 6-membered ring. We can form a CC sigma bonds in place of pi bonds into the product. That is also a good achievement we can call into the Diels-Alder reaction. And also they are stereo specific reaction as well as they have the regioselectivity in the product. If we go further in the stereo aspect of this Diels-Alder reaction, we have to consider the stereo aspect into the starting material itself. We know that as a butadiene will be having a 2 stereo aspect like trans as well as cis, but in the starting material we require a cis material which leads to the formation of cyclization over into the Diels-Alder reaction. Here we can see the S trans conformation is there with the butadiene system, or in the other side we will have a higher energy form of this butadiene over here. But in order to get the cis form, we require a energy to achieve the cis form into the butadiene. Here we can have several examples of different kinds of starting material, and we will have a different respective different products over here. You can see starting from the 1,3-butadiene, and it will react with the ethylene under the certain condition like a 200 degrees centigrade and pressure we can apply. We will have a cyclohexene out of the reaction. Again, we will see 1,3-butadiene, if it reacts with the 3-butene 2-ol as a increasement of here the electronegativity, or we can see the electropositiveness is increased into the dinophile, and we can see the reaction condition also we require a less temperature over here. So again we will have a 6-member ring into the product. So again we can increase the nucleophilicity over the diene as well by putting the electron donor group over the butadiene. As we have the diene as a nucleophilic nature, this nucleophilic nature can be enhanced with the help of donor site, or with the help of putting the donor group over the butadiene group or diene group. Here we have the 2 methyl groups, and here we have the one of the electron withdrawing group over here as a ketone form, and that will be enhancing the speed of the reaction, or we can call as a this reaction will be facilitated, and we will have a product within a 30-degree temperature. As soon as we see this all, as soon as we increase the electron donors on the butadiene system, or if we increase the electron acceptor or electron withdrawing group over the dinophile, we can have increasement, or we can expedite the reaction over here. See, the electron releasing group as such, we know that there are electron releasing group like methyl alkyl group, so, and there are ether groups as well, and ester groups with the coordinating with the oxygen over here, and electron withdrawing groups such as aldehyde, ketones, ester, nitro, and cyano groups are there, which can put over the dinophile, and this one we can put in the on the diene, and we can have a increasement of the or we can facilitate the reaction. Here we can see the another example which is having with the cyclopentadiene over here, and this cyclopentadiene, one of the cyclopentadiene will work as a diene system, whereas one of the cyclopentadiene and one of the group of the cyclopentadiene will work as a dinophile, and we will eventually reach to the cyclopentadiene adduct, where we can have a bicyclo product at the as a stereochemistry is concerned, we have a endo form of the product. We can also see basically how this endo form is looks into the crystallographic structure. Here we will have a cyclopentadiene structure here, basically one, and another cyclopentadiene structure or is attaching over the other side as a endo form, or it's going to the going to the inside of the ring. That we can see, and basically how we can express the exo and endo form. Here we have the outside of the ring, it is exo form, while this we have the inside of the ring, that is your endo form. These are the different forms are there. Because of that we can say that whether this reaction goes to the endo form or exo form with respect to different substrate. Here we have the cyclopentadiene as a diene system, and this is methyl propionate as a dinophile system. Here we will have a endo product again, because of this will be as a electron deficient center, and here we will have a electron rich center, and there will be a attraction between them, so that we will have a attraction between them, and we will end up with the endo product into this type of reaction. Again we can see the different examples over here. We will just replace the dinophile substitution over here, and we will have a corresponding cis product over here. Again we can have a different trans dinophile over here, and we will end up with the trans product into the stereochemistry aspect. If you see, as compared to this one, we can generate cis as well as the trans product. Again, these are the different example where we have the endo product as well as the exo product out of the two reactions. as we consider the example part of this Diels-Alder reaction, we consist of mechanism. Here basically this mechanism goes through the cycloaddition reaction, or we can say as a concerted mechanism. Basically we cannot trap basically our intermediate over here. So whatever the electron flows, it is in concerted manner, or it is in the simultaneous manner, so that we are calling as a concerted pericyclic reaction type. And this, we know that this is the type of pericyclic reaction where we have the 4+2 cycloaddition over here, and we are end up with the 6-member cyclic ring. This is the basically structure which is showing with the cyclopentadiene example, how it will looks like in the crystallographic structure. Then another one dinophile will be there, how we can see the nature of this keto group over here, ester group over here, and how into the plane it looks like. Okay, and the plane of the cyclopentadiene also we can show here, and how it will end up with the endo product, or how it will be end up with the endo system. So this is overall Diels-Alder reaction, which is having with the 6-member cyclic ring. Thank you.